So as Ufu kindly said, my name is Levin. I'm an infrastructure engineer on Stripe's streaming team, and this is a photo of me around a bunch of garbage.
And I'm Mike Mintz. I'm also an infrastructure engineer on Stripe's streaming team, and here is a photo of me disco roller skating. We're going to present an experience report on how Stripe embarked on writing a dual source operator in Flink. We'll start by walking through our motivation, deduplicating Stripe's ledger to make sure no single transaction is applied multiple times. Then we'll examine 3 different approaches to implementing deduplication across all time, none of which we were happy with. Then we'll see how easy it is to write a custom source, followed by 3 big challenges getting it to work correctly for our use case. Finally, we'll recap our solution, chat about some of the lessons we learned along the way, and see how this problem could be much nicer to solve in a future version of Flink.
All right, so let's just kick it off right now by motivating y'all why you should suffer the next 40 minutes with us. All right, so our motivating example for this talk will center around something called deduplication. So a deduplicator is something that takes as input a stream of emojis and outputs a stream of emojis where all the repeated emojis have been removed. As you can see on the your left, my right-hand side here, we have 2 poo emojis, and on the right we have 1 poo emoji. The emojis that have been deduplicated, our deduplicator has been successful. Now, as you can imagine, deduplication is probably important for a financial company like Stripe, especially if you want to provide a real-time ledger. Now, for those who haven't been tortured with financial terminology, a ledger is something that contains all the financial actions against a merchant at Stripe. And we didn't just want to build a real-time ledger, we wanted to build a real-time ledger containing all the financial actions for every merchant on Stripe that allows any developer at Stripe to republish these transactions at any time, for reasons that are beyond the scope of this talk and my psychological health. So here's a few ways we tried to tackle the problem of deduplicating Stripe's ledger in real time. We felt that Flink would be the perfect platform to write our deduplicator. After all, an idyllic deduplicator fits within Flink's model quite well. The plutonic deduplicator starts as a keyed process function. It has a single state variable, seen, that tells us whether we've seen the event or not. In the process element, where we receive an element and then optionally emit one, we simply ask ourselves, have I seen this ledger event before? And if I have not, then I output it and I update the state variable to say that, yes, indeed, I have seen this ledger event now. And the next time one comes, the state variable will be false, saying it'll be true, I will have already seen this, and we will skip the next one, thus deduplicating it. So, if we want to use this operator in a Flink job, we simply need to put it between a source and a sink. But specifically, we have a Kafka source full of a topic with ledger events. We key the ledger events by their ID so that the events with the same ID go to the same subtask of the deduplicator, and then we deduplicate them using the code you saw in the previous slide, and finally sync them into a new Kafka topic with the deduplicated event stream. In Flink code, this looks like exactly what you might expect. We add a source of ledger events, we key them by their ID, we process them through the deduplicator you saw on the previous slide, and then we sync them into a new Kafka topic. And all is well in the world of deduplication. Unfortunately, our ledger had one last gnarly requirement, which was we needed to provide all-time deduplication. You see, if a beautiful little ledger event starts its life in 2012, and then for some Lord knows why reason, a Stripe engineer needs to republish that ledger event in 2019, we need to make sure the output of our deduplicated topic has only the 2012 event and not the 2019 event. And we may need to go back as far as the startup history of time in 2011 to do this. Now, why shouldn't this work? Well, unfortunately, this last requirement means that all of our events need to be in Kafka. And Stripe does not operate Kafka with infinite retention. I wish we did. So if we want to start our deduplicator from Kafka, we have to have all our events in Kafka, and Stripe's retention period on most topics is 3 days. So that didn't really work for us. So while Flink provides all of the primitives for a perfect and idyllic deduplicator, the vanilla Kafka source cannot be used for us because we do not operate Kafka with infinite retention. But that's okay, because whenever Kafka is about to expire events every 3 days, we will dutifully archive them into S3 so that they're not lost forever. And that should mean that maybe we just need to read all the events in S3 through a deduplicator, and then when that's done, read from Kafka. That should be enough to have our deduplicator. So let's see how multiple sources might work in Flink. It turns out they work pretty well. Flink does have a way to combine multiple sources. You can union them together. So, for example, here we have our S3 source, and here's a Kafka source. And if we just call union on one of these sources and union it with the other source, we get a unioned stream of these events. And all should be done, right? Well, as you can probably imagine, that doesn't exactly work. You see, our use case demands order. It would be a little weird if your financial transactions were just rearranged arbitrarily. And so we really need that 2012 event, the first one, to be before that one in 2019. And if you union events, if you union streams in this way, you'll just get all the events at the same time, essentially. And in fact, the order is not even necessarily deterministic. And so this is not an acceptable solution for us. Now, there is a sort of thing you can do. We could have written our deduplicator, which fit on one line of code, on one slide, and maybe made it fit on like 7 slides by making it watermark aware. But this would mean that while the deduplicator would respect time and only emit elements as the watermarks increase, the other events that are constantly being streamed in from our union source would get buffered inside Flink's state. And we have a lot of events, and this was potentially untenable for our Flink cluster. And also didn't seem like a good solution for something that really should just be able to be processed in order.
So let's rewind for a second. We're trying to implement all-time deduplication. We can't just use a Kafka source by itself, since we have limited retention in our Kafka clusters. This means we need to read from 2 sources, Kafka and S3. But combining them with Flink's built-in union operator doesn't work, because either events arrive out of order, or if we use watermarks, events from Kafka get buffered until we finish all files from S3, resulting in potentially a very large Flink state. So maybe we're making this too complicated. We just want to read from S3 first, and then Kafka afterwards. Rather than getting all fancy with unions and watermarks, could we just run 2 separate Flink jobs, one to bootstrap from S3, followed by a second one to continue from Kafka? On the surface, this idea seems pretty straightforward. We'd start with one version of our job using the S3 source, and when it finishes, we'd start another version of the job that's identical, except we'd use a Kafka source instead. However, this manual bootstrapping approach, i.e. running an S3 job to completion followed by running a similar Kafka job, gets more complicated when getting into the details. We would need a way to automatically terminate the S3 job when it's done so that we can move on to running the Kafka job. That means adding something around the S3 source to handle termination logic, adding something around the Kafka sink to also handle termination logic, since we'd need to wait until the events have gone all the way through the deduplication pipeline before we can safely exit. Plus, we'd somehow need to trigger a save point before we exit, which we'd use to initialize the Kafka job from. Now, while it might be possible to implement this for Stripe's ledger deduplicator use case, it's not an easily pluggable solution. It would mean that every Flink job at Stripe would need to incorporate termination detection logic, and it would require maintaining some sort of infrastructure to orchestrate launching 2 jobs sequentially, taking save points. We have many different teams at Stripe with Kafka use cases, and we want it to be easy for all of them to write Flink jobs using historical data. An even bigger issue for manual bootstrapping is that the first job must finish reading data from S3 before the subsequent data on the Kafka topic expires. If our Kafka topic is configured for 3 days of retention, and the first Flink job takes 1 week to get through the historical data in S3, we'll have a gap of 4 days when we cut over to our second Flink job that reads from Kafka. So this wasn't going to work for us. Let's review our options so far. We can't use a vanilla Kafka source because we need to deduplicate overall history, and Kafka has limited retention. We can't use the union operator to combine S3 and Kafka data because our deduplicator would use a huge amount of state buffering up messages from Kafka while it waits for the data from S3 to catch up. And the manual bootstrapping approach is challenging to operate and would require us to finish bootstrapping before Kafka events fall out of retention. But what about just writing our own dual source? Maybe writing sources is hard, but most of the work has already been done for us, since Flink comes with built-in sources for reading from S3 and reading from Kafka. All we have to do is to compose them together using some sort of wrapper source. And this seems like it shouldn't be too hard. In fact, last year at Flink Forward 2018, Lyft presented on this exact problem of bootstrapping from historical data. They walked through the approach for unioning two sources and the approach for manual bootstrapping, but they spent comparatively little time on the approach for writing a combined dual source. Apparently, writing a correct dual source without deduplication is hard. But how hard could it really be? We record our Kafka offsets in our S3 archives, so it should be quite straightforward to cut over from S3 to Kafka without any duplication. Let's see how this might work. First, let's quickly review what a source is. Every Flink job starts with a source. It might be one of many built-in sources, like the Kafka source or the S3 source, or it could be a custom source, like the dual source that we want to build. Sources are similar to, but slightly different from process functions in Flink. At the most basic level, a Flink source just needs a run method. There are a few other methods to implement, but they're really not very important. Anyway, each job's run method is called exactly one time at the beginning of the Flink job, and it just emits records whenever it feels like it. In this case, we have a while true loop, emitting records forever, like you'd expect from a Kafka source, or you could have it terminate if you wanted to write a bounded source, like a file reader. So what about actually writing a dual source? In the run method, it should first start reading all the data from S3, wait until it's done, and then cut over to reading live data from Kafka. Just a few lines of code. Easy, right? Well, no, if it were that easy, we wouldn't be here presenting today. And we can't say that we weren't warned.
So now that you know why we would want to go down this foolish journey, let us tell you some of the hurdles we encountered along the way. The first hurdle we encountered had to do with trying to wrap the underlying S3 source itself, which is itself an input format source function. So here's a sketch of our first attempt at writing the dual source, which just wrapped the S3 source and the Kafka source. It's a source function in its run method. We run the S3 source to completion, and then we run the Kafka source. And if this actually worked, this would get us pretty close to a functioning dual source, but as you can probably imagine, there was a problem, and the problem was in the S3 source, the input format source function. Here I am last year writing an email to the Flink user list, which you heard so much about in the keynote, and I write, hello, I'm trying to write a custom source function which wraps an underlying input format source function. When I try to use this source function in a stream, I get errors related to the input split assigner. Now, the input split assigner is something that Flink does to take a huge S3 file, chop it into chunks, and then distribute it amongst the subtasks. So what's happening here is that we were encountering some kind of bug with how the S3 source, the input format source function, was being initialized. And this is where things get a little bit scary, because I write, I believe the underlying error is related to this call to instance of input format source function. And you know you're having a fun time in the JVM when you hit a bug that's related to casting. And so I knew that I was going to have a fun time trying to figure this out. Now, what was going on is that when Flink receives your job, it takes your job and turns it into a graph. You've seen the graph in the Flink UI. It's a bunch of maps and flap maps and this kinds of stuff. And when it encounters a source, it does something a little bit special to the source because they're the root nodes. And it calls this transform source function. But if your source happens to be an input format source function, it does some super secret special stuff, like initialize the split assigners. And we didn't have an input format source function. We had a regular source function, and that meant our S3 source was not getting properly initialized. Now, I know you're all thinking, well, why didn't you just implement an input format source function? And let me just tell you, we tried to do that too and ran into a bunch of other errors for which I didn't have nice, pretty emails to show you. And it was just a horrible, torturous time. So in the end, we had a few discussions, and we decided that, hey, why have a janky, incorrectly initialized input format source function when we can just manage the S3 files ourselves? We have a lot of internal kernel knowledge of our archives. We know what time and what dates they're coming from and the S3 offsets. So why don't we just do it ourselves? And this turned out to be a lot easier than we thought. Instead of wrapping the input format source function, we just deterministically enumerate the files that we want to process. Then we partition these files based on their index and the subtask ID to distribute these files to various subtasks. And then we reuse Flink's input format structure so that we don't actually have to do the hard work of opening the files and reading the elements. And then we use operator state in our source to track progress through the files. This is almost what the input format source function is doing already. So visually, what this looks like is we deterministically order our set of files that we want to process, our S3 archives full of these ledger events. And then we have here 3 subtasks of our dual source representing one of parallelism 3. And if we want to distribute these files, we just do the modulo of the index and send them over to each little subtask. And one sort of nice property of this is that each subtask is also processing their chunk of the archive in time order too, which is really nice for us. So we were able to wrap our S3 source by not wrapping it at all and managing all the files ourselves and tracking the process in state, which got over our first hurdle that we encountered when trying to build our own dual source. So everything was wonderful, right? We got 23 minutes left. We can all go home? Well, unfortunately, no. Our second hurdle, partially introduced by the first, was that now we hit this gnarly Kafka retention bug. Not bug, but feature, I should say. So an important feature of our solution to the first hurdle was that we managed and distributed the S3 files ourselves. And specifically, the order and number of them was deterministic. And what this meant clearly was that it's always the same, no matter how many times we run the job or resubmit it. And that's great for properties of distributed systems to have things that are basically static knowledge and everyone knows, but it caused us a problem with the Kafka retention. Because what if processing all those files takes 1 week and our retention is only 3 days? It means that when we go to hand over, we're going to miss some data. And nobody wants that. So let me explain visually so that you can really internalize the struggle that we're experiencing. Here is our deterministically ordered set of files that we are reading into our dual source. Suppose this takes one whole human physical time week, 1 week to process in real time, in actual genuine time. And meanwhile, new events are coming into Kafka, and the retention is 3 days. So some of those events in that 1 week that are new are being expired and put into S3. And so when it comes time to do the handover from S3 to Kafka, well, we're going to miss 4 days of events that came in when we started our job and were expired before it finished. And this is not a desirable solution for a dual source. I mean, maybe if some of the credits against your account go missing, you might be a happy merchant, but the other side of the merchants aren't going to be happy. So we can't miss any events for our ledger. So we have a solution, though, and that was to recalculate the end time every time we resubmit the job. So if we could recalculate the end time of the S3 bootstrap every time we submit it, then we should be able to get around this. And let me show you how that works. So again, story is story. We got our deterministically ordered set of files. We read them into our dual source. Taking it takes 1 full week. All the meanwhile, events are being published to Kafka, and they're being expired after 3 days, and we're about to miss them. But now, instead, when we're done the S3 bootstrap, we ask ourselves, I know what the last timestamp of the file was, I know the current time, and I know the retention period of Kafka. I can use these 3 facts to ask myself, am I going to miss events if I hand over now? And if the answer is yes, we simply resubmit the job, and at that time, recalculate the end time of the bootstrap. And now, the job starts back up, it continues processing files, it's processing now the files that we would have missed, and then when it reaches the end of those files, we again ask ourselves, I know the end time of this file, I know the retention period of Kafka, and I know the current time, am I going to miss any events? And if the answer is no, you will not miss any events, well, we hand over to Kafka. and all is wonderful in the world.
So we have reasonable solutions for the S3 side of things, both in terms of wrapping the S3 source itself and making sure that we can cut over before Kafka falls out of retention. But what about wrapping the Kafka source? It would be great to be able to reuse Flink's built-in Kafka source, since it would be quite complicated to re-implement it ourselves. Plus, if we had a generic wrapper source, we'd have the ability to sub in other sources, like Kinesis. In theory, the Kafka source should be easy to wrap, since there are no instance of Kafka special cases in the Flink internals, as we encountered when trying to wrap the S3 source. We should just be able to call the Kafka source's run method once we finish bootstrapping. But it's probably not actually that simple, otherwise I wouldn't be talking about it right now. So why is that? Remember a few minutes ago when I said that there were a few different methods to implement in source, but that run was the only important one and that the others didn't matter? I was wrong. There's actually some other important stuff here. Now, yes, run is the most important, but there's another method that we need to think carefully about, and that method is called initialize state. In fact, the order of these two methods is paramount. Flink's runtime guarantees that the initialize state method is always called before the run method, so that the state from the latest checkpoint or save point is available to the logic in the run method. It's not hard to implement both of these methods sequentially. We can do the S3 portion first, followed by the Kafka portion. So what exactly is the problem? The problem is, before we can initialize the Kafka source, we need to configure which offsets it should start from. And in order to know which offsets it should start from, we need to wait for the S3 bootstrap to finish. But the arrow of time is flowing in the wrong direction. Nothing seems to fit anywhere, no matter how hard we try. And we tried a lot of things, setting the offsets after initializing the state, calling initialize state from the run method, reading S3 files at startup, but none of it really worked for us the way we wanted. But what if there were an easier way? What if we could completely separate our S3 logic from our Kafka logic so that everything in S3 is done before we even initialize Kafka? And no, I'm not talking about going back to the manual bootstrapping approach. Let's see if we can stick with one job, one dual source, but try to completely disentangle the S3 logic from the Kafka logic. So how would this work? First, whenever we initialize our dual source, we should decide whether we're in S3 mode or whether we're in Kafka mode. And we can determine that by examining the operator state, which we're already writing to track our progress through the S3 files. When we start up in S3 mode, we'll just continue reading S3 files like normal. We'll track the progress through the files using the S3 file progress operator state, and we'll track the archived Kafka offsets that we've seen in the S3 max offsets operator state. Then when we start in Kafka mode, we'll just wrap the built-in Kafka source, and since we have the max offsets stored in state now, we can use them to initialize the Kafka source. But how do we get from the end of S3 mode to initializing Kafka mode? Easy. We just have to make sure that the Flink job restarts after we finish all of the files. Of course, we need to wait for a checkpoint before restarting so that our operator state is flushed. Let's see what this all looks like. When our dual source starts up in the initialize state method, we first load our operator state from the latest checkpoint. We get the status of all the S3 files we've been bootstrapping from, as well as the maximum Kafka offsets we've seen in those files. This is enough information to decide whether to start in Kafka mode, and if so, which offsets to start from. Then in our run method, if we're in Kafka mode, we just run the Kafka source. Otherwise, we're in S3 mode, so we run the S3 source logic. We wait for a checkpoint, and then we force the Flink job to restart. But how do we wait for a checkpoint, and how do we trigger the Flink job to restart? Waiting for the next checkpoint is pretty simple, because Flink provides a checkpoint callback, so we just use a Scala promise to block until that checkpoint callback is called back. Now, restarting the Flink job programmatically, how do you do that? Flink doesn't actually offer an API to programmatically restart that job. However, Flink's default failure handling strategy involves restarting a job whenever it throws an exception, so we can just throw an exception. Now, this all makes sense for a source with parallelism set to 1, But how can we possibly coordinate across multiple subtasks, all finishing their S3 bootstrap at slightly different times, but all needing to restart into Kafka mode at the same time? And we can't use any of Flink's cool distributed operators like keyby, since we're implementing a source. Now, lucky for us, Flink has a feature that we can abuse to get distributed coordination in any operator, including sources. And that feature is called operator state, specifically union list state, and we've been using it all along. During startup, every subtask gets to read the union state from every other subtask, and this allows us to periodically restart, checking the operator state each time until every single subtask has finally finished reading from S3 before we start going into Kafka, ensuring that we get into Kafka mode atomically. Finally, we're able to have a source that can read from S3, seamlessly cut over to Kafka without worrying about falling out of retention, and read from Kafka using the built-in Kafka source.
Seamless. How did we get here? So, now that we have a dual source that meets all our requirements, let's have a little recap so you all are refreshed. We started by needing to deduplicate to provide a real-time deduplicated ledger. And we wanted our application to look something like this, where we read from Kafka and output to Kafka. But because Stripe did not operate Kafka with infinite retention, we had to read from both S3 and Kafka in order to provide a deduplicated stream. But that's okay, because we could bootstrap from S3 and then hand over to Kafka when we're done, and that led us to develop our dual source. Ignoring sage advice from our peers at Lyft, we embarked on building this ourselves, and we encountered 3 hurdles along the way. The first hurdle had to do with wrapping the S3 source itself. There was a bug initializing the input format source function because we were not an input format source function. And we solved this by simply deterministically ordering and distributing and managing all the files ourselves. The second hurdle was introduced partly by the first and had to do with the the retention period in Kafka. If we did it naively, we would miss a bunch of events when we want to switch. And we solved this by resubmitting the job and recalculating the end time whenever we get close to Kafka, and only doing it when we're assured that we're going to be safe. The last hurdle we encountered had to do with wrapping the Kafka source. When we initialize the Kafka source, we need the offsets, but we can't get the offsets until the S3 part is done, but you don't initialize before the S3 part is done, so everything didn't work. And we solved this by introducing a S3 mode and Kafka mode and using Flink's restart policy to coordinate between the subtasks and ensure that they atomically switch between S3 and Kafka. And finally, we're able to have a source that can read from S3 seamlessly, cut over Kafka, and read from Kafka using the built-in source. So specifically, our dual source does the following. It reads events from S3. It reads from Kafka when it's finished reading events from S3. It does this by delineating between an S3 mode and a Kafka mode. It keeps a bootstrap end time state variable, which is updated every time it's resubmitted, unless we're in Kafka mode, and then it never updates it again. And we coordinate by subtasks to do the handover by storing progress in operator state. And the handover looks like the following. Upon S3 completion, we block until there's a checkpoint, and then throw an exception to restart the trigger. And for all you Berliners out there, I know that what you're saying right now is, genau. That makes a lot of sense.
Except there was one caveat with our solution that took us a while to realize. And this was that different subtasks can make progress on the S3 files at different rates. This was the result of an explicit decision we made early on, which was to deterministically decide which subtasks work on which S3 files and have all the subtasks make their way through their lists of files independently. This might seem perfectly natural, but this was actually a subtle departure from Flink's built-in input format source function, where there's a single iterator of S3 files, and all subtasks lazily pull from that same iterator. So that's all well and good, but why is this a problem? And for simple jobs, this isn't much of a problem at all. But for use cases that require ordering, like our ledger deduplicator, independent subtasks lead to watermark skew, which can potentially fill up Flink's state. Let's see what this looks like. Here is our job at startup before it has processed any files. All of the watermarks are uninitialized. First, the dual source subtasks both pick up their first assigned files, day 1 for subtask 1, and day 2 for subtask 2. Then let's say that they both finish processing their first files around the same time, so the ledger events start to get processed in the deduplicator operator. But remember that our job is watermark aware, so we need to see how those watermarks get set. Our dual source's first subtask has processed all of its assigned days up through day 1, so it emits a watermark for day 1. Likewise, its second subtask has processed all of its assigned days up through day 2, so it emits a watermark for day 2. And since the deduplicator is downstream of a key-by operator, it sees the minimum watermark in the dual source, which is on day 1. The deduplicator can now safely emit records from day 1 to the Kafka sink, but it must buffer up the records from day 2 in the Flink state until its minimum watermark reaches day 2. So that's not too bad, just buffering up 1 day's worth of events. But let's see how this progresses when the second subtask is very slow, maybe because one of the S3 files that we have was unusually large. So first, each subtask takes its next assigned file, day 3 for subtask 1, and day 4 for subtask 2. This time, only the first subtask makes progress, so the ledger events start to get processed in the deduplicator operator. Here we see the first subtask emitting a watermark for day 3, and now the deduplicator's minimum watermark has reached day 2. And because of this new watermark, the deduplicator can now safely emit records from day 2, which it had buffered in state, but it now must buffer up the records from day 3 in the Flink state. And let's say subtask 1 quickly makes progress through its next 2 assigned files, days 5 and 7, emitting a watermark for day 7, and now the deduplicator's minimum watermark is only on day 4. Wait, did I do that right? Yes, here we go. So we get to emit records to Kafka for days 3 and 4, but because one of the subtasks is slow, all of the latest records from the faster subtask has to get buffered in state. Now, in practice, this buffering isn't quite as bad as the buffering we'd get in the union approach we explored earlier, and it's possible to mitigate by temporarily dropping the parallelism on the job. But this watermark skew could have been avoided if we had been able to use Flink's built-in input format source function in our dual source. This built-in source is able to share a single iterator of S3 files among all of its subtasks, sort of a work-stealing approach, so they can all be working on the latest files around the same times. Although we can't reuse input format source function in our dual source for reasons, there is an active Flink improvement proposal that could make this approach feasible.
So let's go over some lessons that we learned so that you do not have to suffer as we have done here. The first lesson that we learned implementing this dual source is that there truly is a difference in experience between polymorphism and pattern matching. If you want your universe to be openly extensible, prefer polymorphism. This would have avoided this instance of issue with input format source function, and I believe that Flink does want the community to build other sources. The next is hubris. When somebody says something is hard, just really believe them. It's not that we didn't believe Lyft when they said it was hard, but there was definitely, upon reflection, an element of, hey, they didn't really spend much time on this weird, obscure technique. That must, that can't be that difficult. And certainly it was. Coordination in distributed systems is hard. That's something you should always remember. We had to abuse Flink's restart policy just to ensure that the S3 to Kafka handover was atomic. And sources are hard. Put as much into operators as you can. Operators are composable and sources are not, and there's really not a simple way to just wrap source. And the last thing is that you should all use the mailing list. I got so much help and support from the community, and I complained so many times that Ufuk took me out for lunch when I visited in Berlin in April, and I guarantee he'll do that for you also. Right? Just joking, but maybe. All right.
So one thing that we saw on the mailing list was that we weren't the only ones having trouble implementing sources in Flink. In fact, there is a proposal, Flip 27, to refactor the source interface in Flink. And while this isn't available in the latest version of Flink, it could greatly simplify the implementation of a dual source. One thing this proposal does is to split sources into 2 sequential operators, the split enumerator and the reader. This would potentially allow us to wrap existing S3 and Kafka readers and write a relatively straightforward custom split enumerator to control them. Our custom split enumerator would omit splits for each file on S3 in order, wait for the S3 readers to finish processing them, and then omit splits for the Kafka reader. And then our custom source reader would just wrap the S3 readers and Kafka readers, pattern matching on the type of the split it receives. While our current solution works fine for us in production today, we're excited about the prospect of simplifying our abstractions as Flink evolves nicer interfaces.
So we have only a little bit of time, I think, for questions. But what Mike and I did want to say is that probably a lot of you have a lot of thoughts about this. And if you want to talk to us outside of this, you can also do that. So please feel free. But I guess now we can hear your laments.
Thank you.
Thank you.
A potentially maybe really obvious or dumb question. As opposed to triggering the job restart, did you consider like sort of the first option where you could have triggered the second, like there could be two separate jobs for S3 mode and Kafka mode, and then the end of the first job could actually make a call to the job manager, which allows a job start and actually then start up the second job?
I think...
I mean, one thing that we were concerned about was making it very easy for anyone at our company to be able to just plug this into their job, and having them to have to run two separate jobs felt like it would be quite a big burden. So we didn't spend too much time exploring that path, but it's possible it could have been easier overall after we'd learned what we'd learned about doing it this way.
Yeah, I mean, I think we definitely explored a lot of different options, and some were called for reasons that aren't very interesting, like doesn't fit into our deployment model, or like, you know, all these things. One interesting challenge about the idea of doing an API call at the end of a job to the job manager is that you run into this small but potential issue of, if something goes wrong, launching more than one job. And then if you're launching more than one job that's doing deduplication and syncing into the same topic, you've possibly broken the semantics of your deduplicated topic. So that would be probably the one thing that I would be concerned about, but otherwise that might actually work out pretty well. I think in this, during this work, during the presentation, there was a lot of like, even Mike and I being like, well, didn't we think about doing it this way? Like, what if somebody asks us this question? And we're like, oh, maybe we did. And, you know, there's a lot of options to go through, and it's kind of an interesting design space. And I would say that it's probably, if any of you are like, hey, did you do this? You should come and ask, because either we didn't, and then we should just really make this a lot simpler, or we tried it and it didn't work for whatever reason. Thank you.
Thanks.
Also, possibly a dumb question. How are you handling out-of-order events coming into your Kafka source?
How are we handling which kind?
Out-of-order events?
So if you're reading from multiple Kafka partitions, presumably the same key can come in different partitions. Are you handling that?
So this particular use case, they only care about out of order at a large scale, like on the order of minutes or hours or days. They really didn't want us to replay the data and get the 2017 event instead of the 2012 event, but they were totally okay with one Kafka partition being behind by a few seconds and that happening. But that being said, because we had to implement watermarks for this solution to get S3 and Kafka to work at the same time, the actual deduplicator that we're running does buffer things up and wait for watermarks, and I believe that the Kafka tracks separate watermarks for each of its partitions, so that if one of the partitions is ahead of the other ones, the minimum watermark that gets into the deduplicator will just be waiting, and things will get buffered up. So at the end of the day, our deduplicator will fall behind while it waits for things to get in order, as opposed to play things out of order, which is not necessarily the behavior that we want, but we generally don't have too much skew in terms of our Kafka partitions. Yeah. These aren't key Kafka topics.
Good question.
So not directly related to the talk, but regarding the delivery guarantees, we talk about at least once, at most once, and exactly once. And usually we say that in case of financial transactions, we go for exactly once. So in Stripe, do you always go for exactly once, or is it based on the use case you decide?
For this one, it's for this particular job, it's exactly once, but we have we have one other very important job that's not exactly once, and then one important job that I think we are running it under exactly once, but not guaranteeing it is to anyone. But for this one was specifically exactly once. But there's other money movement things happening at Stripe. So
Okay.
Yeah, and we also, the things that are at least once typically have idempotent things downstream of them, so they don't really care and they're okay replaying data.
yeah.
Thank you.
So if your deduplicator falls under back pressure and falls out of the Kafka retention period, is that automatically going back to S3?
Yeah, so this is something we somewhat elided in the talk, but we have a very easy deployment situation with Flink at Stripe, so people just run a command and then the job gets updated. And so we have a graph for how far behind it is, and like a warning sign, like if you don't redeploy the job, it'll miss events. And so basically it's somewhat seamless in the sense that you don't have to do any work, but like getting closer to the end of the job, you need to pay attention to this graph and possibly redeploy it. So if one is not on top of this a little bit, then it will hand over and miss events. Although I think we might have some assertions that will crash the job possibly.
Yeah.
Yeah. Because we know where the last watermark is. So if the first thing that comes from Kafka is not that, we'll crash.
Cool. Then the last question here from Robert.
So how did this restart-based coordination approach work with the growing state size of the deduplication operator? Because probably over time, the deduplication operator needs to store more information on the records. Did you use the local recovery of Flink, or how did this work?
So I think it would not work on local, or okay, the local recovery meaning the state is still on the task managers? Yes, that's enabled. We didn't see that many problems with the actual restart thing. And in fact, I think our restart policy here is worse than what we presented. Like I think it's we could make it less aggressive, but it seemed to hand over fine the 2 times we ran it.
Yeah, I mean, in general, it is a problem that our state keeps growing unboundedly. Like, it's not just these restarts, but also we want to like redeploy to change the parallelism because we want to run our backfill like very high parallelism. And once it switches over, we'd rather like size down to a smaller thing for efficiency. And as our state grows and grows and grows, this becomes scarier. But so far, it's okay. But we are like actively looking for solutions for like having faster restarts with large state.
Yeah, we want it all.
Yeah.
Thank you, everyone.